One of the few truly creative parts of solving a classical mechanics problem is where you get to choose your coordinates. And we could choose, say, that the position of this mass on the rod there was described by Cartesian coordinates. We can have an x and a y. Problem with that is that actually the position of the rod is therefore a fairly nasty function, a sort of arctan of the ratio of those things. And so to keep things a little bit simpler on that front, what we might do instead is pick, say, the position of that mass is its q along there, and we might also pick that the position of the rod is a particular angle down. And those are very natural coordinates for this problem, and all we have to do is convert between them. Because we know we need to convert between them, let's just do that now. So we've got x, the position x of this mass in terms of this is going to be q sine theta. And the position, the y position, is going to be q cos theta. We check the signs on that, so when theta is 90 degrees, this is going to be q over to the right, and when theta is 0, that's going to be q up top, so that's good. Okay. So now we want to know the Lagrangian, which remember is just the kinetic energy minus the potential energy of the whole system. So you have one Lagrangian for your system, not for each particle. So we've got the total kinetic energy and the total potential energy. We need to know the kinetic energy of this thing here, and we realize that actually we're missing some things on our diagram. Whenever you introduce a quantity, you've got to put it on your diagram so you don't then forget what it is. So I'm going to have the mass of my object there being m1. I'm going to have the mass of my rod being m2. I'm also going to need to know the moment of inertia of my rod, so I'll just write that as I. Because I'm going to have the potential energy of the rod, I'm also going to need to know another quantity, which is where is the center of mass of the rod. So if that center of mass of the rod is there, then I'm going to write that as L center of mass. Okay. I'm also, if I've got the potential energy, I also need the potential energy from the spring. So I'm going to need yet another quantity, which is where is the natural length of the spring. So I'll have capital L being the natural length. Oh, I better not use L, I better use curly L again. S for the natural length of the spring. Okay, and since I put all those things on my diagram, I might want to put it in words. But at least I've written them down. I've got a center of mass and S to make that kind of clear. Alright, so I want to calculate these terms. And the kinetic energy is going to be fairly easy in terms of the rod, because it's just in terms of moment of inertia, half I times the angular velocity, and the angular velocity is of course theta dot squared. Well, theta dot, and we have to square it. I'm also going to need the kinetic energy of this bead, and I know the kinetic energy of the bead in terms of x squared and y squared. It's the sum of the squares of the velocities in the two directions. And I'm going to need minus my potential, and I'm going to keep that minus sign out there so I don't make any minus sign errors. I've got the gravitational potential of my mass, which is going to be m1 gy. I'm going to have the gravitational potential of the rod, which is going to be m2, this length I just introduced. And I'm going to be, just like that, it's going to be cos theta. And I'm also going to have the potential energy of the spring, which I can write as a half k for the spring. So I've got, oh my goodness, I've got yet another quantity. So this spring has a spring potential of k. So it's going to be x squared. So it's going to be the length minus the natural length, all squared. So there's my Lagrangian. So all these terms, I've got a y here, and I've got x dot and y dots, so I'm going to need to work those out. So I'll do x dot and y dot before I carry on. Now x dot, remember that q is a function of time, but now also theta is a function of time. So to take the derivative, I'm going to need to do a product rule, q dot sine theta plus q cos theta, theta dot. And y, again, I've got a product rule to do there, so I'm going to get q dot cos theta plus q, and I'm going to get a minus sign now, so a minus sine theta, theta dot. And now I can plug all of that into my Lagrangian. Now we've got a lot of sine squared plus cos squared terms, and some of them are equivalent. So we've got a q dot squared, sine squared plus cos squared. We've got a q squared theta dot squared, cos squared plus sine squared. So the fact that sine squared theta plus cos squared theta equals 1 is going to simplify that a lot. And of course this whole term here actually cancels with that whole term there. I've forgotten my g there. Now I must say that the reason I spotted that I'd forgotten my g there was because I suddenly realized that I was going to have to remind you to check your units. So there's our Lagrangian. It's in terms of our q's and our thetas only. And the next thing we do is we check units. Yes, that's units of energy. That's units of energy. This is length squared per time squared. So that's velocity squared. So that's energy. That's units of energy. We've got mgh. That's units of energy. And that's units of energy. So all the units are good. And we could then check limits as well. Now, every year I teach people how to do Lagrangian mechanics problems, and every year people have a go, and every year in the exam people have troubles. And I'm going to tell you why people have troubles. People have troubles because they don't check limits, people have troubles because they don't check units, and people also have troubles because, as you can see, the algebra in this problem is a little bit, well, it's not that hard, but it's a little bit non-trivial to do in an exam. In an exam, when your mind goes blank, it's easy to get things wrong. That is why I have evolved to write things out the way I have, to explicitly write out the coordinate transforms between my x's and y's and my generalized coordinates, to explicitly write out my derivatives. The more you do in your head, the more likely you're going to have troubles. I know many of you are clever people who are going to forcibly do things in your head anyway, and maybe you'll do fine. But I'm encouraging you, especially early on, to really follow this system. Really write out your diagram, put everything on your diagram, write out your coordinate transforms, and then check your Lagrangian before you proceed. To proceed, we go on to our Euler-Lagrange equations. We only have two coordinates, so we only have two equations. So now to execute, I'll do the first term. I've only got one term that depends on q dot, so this first term is very easy. But I have 1, 2, 3 terms with a q in it. And because of that minus sign, I'm going to put a bracket here because I can see there's going to be trouble. That one, this one. There we go. And for the other one, we have only one theta dot. No, we have two theta dots. And notice even that amount of algebra in my head, I struggled. I was going slower. And in a tight situation, I might well have made a mistake. I have two terms that depend on theta. There we go. Two equations, indeed two unknowns. Now this term I've got two things that depend on time, so when I take my derivative I need a product rule. So there are my two equations, call them equation 1 and equation 2. Check units. Alright, so I've got a mass times acceleration. It's a length and time, inverse time squared, so that's also an acceleration, and that's acceleration. Here I have a force. It's classical Hooke's law, so force and mass times acceleration units agree. Here I've got I times theta double dot, which is actually an ml squared, so that's mass times velocity squared. There's a mass, there's a velocity, and that together makes another velocity. That's length squared on time squared, that's another velocity squared. I've got mass times acceleration and another q, so that's velocity squared. And I've got the same kind of term there. So yes, my units agree. I can again check my limits, and that's how we do these equations. And again, try and follow a format very like that when you do your own problems, or you're much more likely to hit errors and miss major mistakes.